everybody, welcome back to Linear Algebra with me. Today we're talking about the inverse of a matrix and the inverse matrix theorem. Big idea for today is last time we did matrix times matrix, and today we're going to undo matrix multiplication. Why are we doing that? Because recall, for a constant, we have like c times 1 over c is going to be equal to 1, so we can undo it. We can also say that it's c times c to the -1 power. And then notice that -1 power shows up for inverses, like for trig functions and stuff. So today we're going to answer the question, can we undo matrix multiplication? The answer is only sometimes. We're going to get comfortable with matrix inverses first, and then we're going to discuss when and how to find matrix inverses in a second. Okay, so first definition. We've got a matrix that is square. It is n by n. It is invertible or non-singular if there exists another square matrix B such that we can multiply it on either side of A and get the inverse matrix. We call B the inverse of A and denote it B equals A to the -1 power. Shocker. If no such matrix exists, we call A singular or not invertible. So the reasoning behind that briefly, for A needing to be square is, let's say that we didn't have a square matrix, it was n by n, then we would have to multiply it by an n by m matrix in order to get the identity matrix. But then as soon as we multiply it on the other side, so n by m, A is m by n. Let's say we were lucky enough to still get the identity matrix. We have an identity matrix that is different sizes, and so they're not the same identity. And so that's kind of like the brief justification behind why we want it to be square. Okay, so let's look at some inverses real quick. Obviously, the identity matrix is its own inverse. That's because when you write it down, identity matrix always gives whatever it's being multiplied back. And so that would be itself in this case, and you can do it on either side. Okay. Sometimes matrix inverses look very intuitive. So for instance, in number B, the inverse of A is this guy right here. We have a half, we have 1, we have -1/3. And we're like, yeah, that kind of makes sense. Let's multiply them together and make sure that it actually works. So we've got 2, 0, 0, 0, 1, 0, 0, 0, -3. Multiplied by a half, 0, 0, 0, 1, 0, 0, 0, -3. Okay, so remember matrix multiplication, we take column 1 times row 1, and that's going to give us, no, where did my highlight go? The first entry in our result matrix. So 1/2 times 2 is 1, and then everything else was 0. And then notice when you multiply that first column by the next row, you're going to get 0. And then same thing happens for the third row. You're going to get 0 for everything. Okay. And then next one, we take column 2 and we do row 1 is going to be 0. Row 2 will be 1. Row 3, you're going to get 0. And so 0, 1, 0. So far, so good. And then we take the last column. And when we multiply that times the top, you get 0, 0, 0. So that's a 0. The middle one, you're going to get 0, 0, 0. And then the last one, the only thing that combines is that -3 and -1/3. So perfect. We get the identity matrix. Okay. Sometimes, most of the time, the inverse is not so obvious looking. So like in example 1C, we're going to do A times A inverse, and we're just going to check that this is indeed correct. That's A inverse. Okay, so matrix multiplication. Row 1, column 1 gives us the first entry. So that's going to be 6 minus 5. And then we're going to go after row number 2. And that's going to be -2 plus 2. Okay, good. And then we do column 2 to get column 2 of our result matrix. So row 1 gives us the first entry. So 15 minus 15. And then we do the second row. That's going to be -5. Why does it keep doing that? Okay, -5 plus 6. I don't know. It doesn't like me switching between things. Okay, we simplify, and we do indeed get the identity matrix. So would there have been a more obvious choice for the inverse of A in 1C? Or is there only one inverse? So glad you asked. Lemma 1, if A is invertible, then the inverse is going to be unique. And we've got a cute little proof for that. We're going to say that B and C are inverses of A. So we're going to start with B. You can write B as B times the identity matrix. But then we know that A times C is going to be the identity matrix because A times C, or C is the inverse of A. So right here, that's just the identity matrix. Then I can redistribute my parentheses, but B times A is also the identity matrix because B is the inverse of A as well. So that's just the identity matrix times C, which we know is just C. So that means B is equal to C. Therefore, you can't have two different inverse matrices, because if you have B and C, and they're both inverses of A, then B ends up equaling C. So why are invertible matrices useful? Well, let's say we've got A and it is invertible. Then what we're going to have is AX equals B has unique solutions for every B in Rn. How do we know it has a unique solution? Well, we're going to have AX equals B, and then I can multiply A inverse on both sides. But then what we've got is the identity matrix on the left-hand side. So IN X equals, A inverse B. So then X equals A inverse B. And we know that is unique because I know that A inverse is unique and B was given, so he's set in stone. So therefore, that's the only possible thing that X can be. Let's take this for a run. Let's say I wanted to solve this system of equations in example 2. I'm going to write this in matrix equation form. I'm not writing it as an augmented matrix because I want to take our theorem for a run. I always do that. Okay. So what I can do is I can just multiply B by A inverse. And I am going to tell you that A inverse is 2/3, 1/3, 1/3, 2/3. This guy right here, that's A inverse. And this was A. There we go. So that means we've got x1, x2, and if we matrix multiply this out, that's going to be 2 plus 2, and then 1 plus 4. So the result is 4, 5. And then if you want, you can plug that back in just to verify that I am indeed not lying, that that is the solution. Okay. But that's only useful if you have A inverse. So how do you get A inverse? I'm going to answer that question in just one more slide. I want to talk about some properties of A inverse, and then I'm going to answer that question so bear with me. Theorem 6, properties of invertible matrices. Number 1, the inverse of A inverse is A. Not shocking. All you have to do is, to verify this, multiply it on both sides and make sure you're going to get the identity matrix. So A inverse times A is indeed the identity matrix. And then if we multiply A on the other side of A inverse, you're still going to get the identity matrix. You get that directly from A inverse being the inverse of A. Okay. Number 2, maybe less intuitive. So you've got the inverse of AB. So that means I'm going to take AB. Now I want to know what his inverse is. So according to this theorem, you can distribute that inverse by flipping the order of B and A. So let's check. If we do that, we get this. And then we can group up these B's here in the middle and be like, oh, well, B inverse times B, that's going to be the identity matrix. That's fine. And then the identity matrix just multiplies with either A or A inverse, and it gives back the matrix that we started with. So cool. So it worked in that when we did it on the right side. So we have to make sure that AB's inverse, we have to be able to multiply it on the other side of AB as well, like this. So there we go. We've got its inverse is on the left side of AB now. So let's check. If we do that inverse distribute, flip the AB, does that work? So B inverse, A, B. Oh. So now our A's are grouped up. So that's going to be B inverse times I times B. And then you just get back whatever you multiply the identity matrix with. Okay. So it worked that way too. And that's the reason we have to flip them. Otherwise, you end up with like A times B inverse, and that's not the identity matrix. Okay? And then the inverse of A transpose is the same thing as A inverse transpose. Let's check it. I have A transpose, and I would like to know what if so I've got A. we've got A transpose, and we're going to multiply it by the inverse of A transpose. According to property number 3, we can switch the transpose and inverse. So A transpose times A inverse transpose. And we're like, okay, is that still going to give us I? Well, we're going to use properties of transposes. Remember, for transposes, you also had that weird switch the order in order to pull the transpose out as well. So I went ahead and did that. And then that is going to be equal to the identity matrix transposed, because we've got A inverse times A. That's the identity matrix. But the transpose of the identity matrix is just itself. Okay, it worked on the right side. Now we're going to try multiplying A transpose's inverse on the left. Okay, so we're going to go ahead. We're going to do the property. We're going to switch it. And then we're going to do times A transpose. And then once again, we can do the switcheroo with our matrices to pull our transpose out. But then that's A times A inverse, which is just the identity matrix. And then the transpose of the identity matrix is still itself. All right, so we have verified all 3 properties in Theorem 5. Okay, now, as promised, how do we find A inverse? So recall, first of all, that A is going to be invertible. Implies that AX equals B always has a unique solution. So, what does that mean? It means first off, having a solution for all B means pivot in every row. That's Theorem 1.4 again for you. Having a unique solution. So that's the other piece. So we've got always gave us this first one, and then unique is going to give us this one here. So unique solution means no free variables. It means pivot in every column. So A is square on top of it all. So we're going to say 1, 2, and 3. So we've got pivot in every row, pivot in every column, and A is square. If we put all those guys together, what we get is if we put A in reduced row echelon form, then A goes through some row operations, and we get pivot in every column, every row, and then those pivots are going to be 1 because our leading terms have to be 1 in reduced echelon form, and that's just the identity matrix. So Theorem 7, A is invertible if and only if it's row equivalent to the identity matrix I. Why is that? Brief connecting of dots. We've already proved it. We said that if it's invertible, it has a unique solution. If it has a unique solution, then this is the only way A can look. Okay. How does this help with finding the inverse of A? That's what I promised you. Okay, we're getting there. Let's suppose that A is invertible. That means we have A inverse. And I'm going to say it has this form. It has columns x1, x2, all the way up to xn, and we don't know what they are. How can we find them? Okay. What we do know, we know A times A inverse equals the identity matrix. That is a thing we know. I know things about vector or matrix multiplication. So I'm going to rewrite A times A inverse as this. Right? That's the definition of matrix multiplication. So each column of A inverse has been multiplied with A. Those are going to be the columns of our new matrix. And then we also have a fun way to write the identity matrix, and that's the E basis vectors. Okay? So in order for these two sides, so left side, right side, in order for those to be equal, we need each column to be equal. So then I can say that AX1 needs to be equal to E1. All the way out to AXN needs to be equal to EN. So all of our columns have to be equal. So that means I am going to solve this augmented matrix and all the other augmented matrices. So I got to solve n many of these augmented matrices. Well, what we want to do is, in order to solve them, is we're going to get A into reduced echelon form, which since it's invertible, we know that theorem's coming back to us. It's going to row reduce. So we're going to do some row reduce, and that's going to give us the identity matrix for A. But what does that give us on the right? Well, hopefully it gives us the inverse, right? We're looking for the inverse. Remember back up here? I said let's solve the equation AX equals E, which means we solve that augmented matrix, which means when you get A into when you row reduce A, you'll get the identity matrix, and it should be equal to the answer. There we go. And we're going to row reduce all of them and get the identity matrix for all of them. Oh, I put 1 and N. Sorry. There we go. But why are we doing the row reductions n different times? It's not going to change. A is what's sitting on the left side right here. And so in order to row reduce it into the identity matrix, you can just use the same operations over and over and over. The only thing that's going to change is the right-hand side. So we are going to be lazy. What we're going to do is we're going to do A augmented, and we're going to put all of the E's on the left. That way we don't have to row reduce A n different times. We'll say lazy way. No, we're efficient people. The efficient way is to put all of the E's on the right-hand side. This is okay because row operations don't intermix columns. And so E1 isn't going to talk to E2. E2 isn't going to talk to any of the other E's because we're just multiplying by constants. We're adding rows together. So columns stay together. So they're not going to be mixing up. Nothing funny is going to be happening. This is okay to do. Okay. So then this is just, remember what the E's are. They're just the identity matrix. So then when we row reduce, remember we get to this here, which is going to be I on the left side. A reduces to I. And then we get all the X's that we want on the left. Oh, but what are all those X's? All those X's our A inverse. So this is going to be IN reduces to A inverse. Okay, summary. How do we find A inverse? You write the augmented matrix, A on the left, I on the right. You start row reducing. You're trying to get A into reduced row echelon form. If there's a row of zeros on the left-hand side, you need to stop. A is singular. It is not invertible. Having a row of zeros is equivalent to saying that A doesn't have a unique solution. I already proved to you that if A is invertible, there is a unique solution. So rows of zeros mean no unique solution, not invertible. Stop. Suppose you don't run into that problem. Let's say we actually get to the row reduced form. That means you should have identity matrix on the left, A inverse on the right. You can use it to like wow your friends or something. I don't know, I felt like I needed a fourth step. Okay, so now that that's out of the way, let's take this for a run. We want to find A inverse for the suggested A matrix. So we're going to take A, we're going to turn it into an augmented matrix with the identity matrix on the right. Okay. So first thing I'm going to do is I'm going to take row 2 and add row 1 to it so I can get rid of that guy. Okay. So row 1 stays the same. Row 2 will change, but row 3 will stay the same. Okay, so row 2 plus R1, that's going to be a 0, a 0, a -1, a 1, a 1, a 0. Okay. Be sure you're watching your right-hand side. The first time I did this, I forgot about the right-hand side. Whoops. Okay. And now I am going to do a 1/2 of R1 to get rid of that coefficient of 2. And I'm going to switch R2 and R3. Okay, so row 1 gets multiplied by 1/2. Don't forget the right. Okay? And then row 2, row 3 switch. 0, -1, 2. And then 0, 0, 1. 0, 0, -1. 1, 1, 0. Okay. I'm going to do negative of row 2 and negative of row 3 because I don't want to deal with the negatives. So row 1 stays the same. And now for row 2, it's 1, -2, 0, 0, -1, 0, 0, 1, -1, -1, 0. Okay. We're doing pretty good. This is pretty close. Let's get rid of this -2 here next. So we can do row 2 plus 2 times row 3. And we're going to get row 1 stays the same. 0, 0. Then row 3 stays the same. But row 2 becomes 0, 1, 0, -2, -2, -1. And then now we only have one step left. We've got to get rid of that -1. So row 1 plus row 2. That's going to be row 3 stays the same. Row 2 stays the same. Row 1 is going to be 1, 0, 0, -3/2, -2, -1. And remember, that is going to be equivalent to the identity matrix on the left, which we do indeed have, which means we now have A inverse on the right. So then A inverse is equal to -3/2, -2, -1, -2, -2, -1, -1, -1, 0. So examples 3, we have found A inverse, go us. We didn't run into any 0 rows, which means we would have needed to stop. Hallelujah. We got to see this in motion. Okay. Cool. Something we talked about at the end of last week. We talked about linear transformations. So we've seen that A having certain properties kind of ends up meaning that T is going to have some interesting properties. So let's see what happens when we apply this to linear maps. What can we say about the linear map T if its standard matrix A is invertible? Spoiler alert, it's going to be invertible as well. But we're going to start with the definition and prove that later. So we're going to call a linear map T invertible if there exists a map S such that when you do composition of functions both directions, you end up getting the just the x vector back. So nothing has happened to the x vector, which means S has undone whatever T did. If this is the case, we say that S is the inverse of T, and we say it is equal to T to the -1. There we go, using -1 as inverse notation again. Okay. So that brings us to Theorem 9. We've got a linear map T is invertible if and only if its standard matrix is invertible as well. And in this case, S ends up having standard matrix A inverse. Shocking, right? Who saw that connection coming? And we're going to prove it. Okay. I think it's easier to start with the matrix side. So A invertible implies T is invertible, simply because we started with matrices before we moved into functions. So we're going to go with assume A is invertible. Invertible. There we go. It's either invertible or invisible. And define S from Rn to Rn by S of X equals A inverse times X. So what we need to prove is that T is also invertible. To get T is invertible, we need this composition of functions to hopefully equal just the x vector, and also this composition of functions to also equal just the x vector. Okay, so we're going to take this back to matrices in order to prove it. So I told you that S was equal to A inverse. So there we go. And then T takes its input and multiplies it by A. So you've got A inverse times X. And we can move those parentheses around. So that's I times x, which is just x. Cool. And hopefully you can see that pretty much the exact same thing is going to happen over here. Aha. So that means T is invertible. And furthermore, S is going to be the inverse of T. Cool. Now it's time to go the other direction. We're going to start with T is invertible and show that A is invertible. So going forward, basically, we're going to assume T is invertible. With standard matrix A. So many words. Let S inverse equal, or let S equal T inverse have standard matrix B. Okay. So then what we know is for all B in Rm, we have T of S equals B, because S is the inverse of T, so we can write T of S of B and still get back B. So then we're going to get A times B, because B is what we defined S to be. It's going to be equal to B. So what we know from here is then AX equals B always has a solution. Specifically, that solution is B. So that's how we know that it always has a solution, is because this B times B vector is going to be the solution. So for all B in Rn. Oh, I have an M over here. That one should have been an N. My bad. So then that means A has a pivot in every row. That was Theorem 1.4. Once again, we use that a lot. So since A is square, it must have a pivot in every column. So at first you might have been very confused at what I was doing, but hopefully you see where this is going now. If you don't, pause this, try and think about it for a moment, because we're almost at the end. Let's see, it must have a pivot in every column. So it is row equivalent to the identity matrix. Thus, A is invertible by theorem, what was it, 7? Yeah, I'm pretty sure it was 7. Okay, there we go. QED. Oh, my box is too wide. It annoys me. It should be cute and tiny. Okay, so there we have it. A is invertible if and only if its standard linear map, or the map with standard matrix A, is also invertible. Okay. We've seen a lot of things that tie back to A having like n pivot points, or AX equal B having a solution, AX equals B having a unique solution. A lot of things tie into this. And so what we're going to do is, you'll notice I keep using this Theorem 1.4. Also remember I said we were going to build on it. It is now time to build on it. Welcome to the invertible matrix theorem. The following statements are all equivalent when we're talking about a square matrix A. So we've got, if A is invertible, we have this laundry list of things. You've got like the equation AX equals B has a unique solution for all B. We have the columns of A span Rn. A has n pivot points. Those should sound familiar. This is basically just theorem 0.14 right here for you. Then you get the equation AX equals 0 only has a trivial solution. We have the columns of A form a linearly independent set. We have linear transformations are onto and one-to-one. We have its row equivalent to the identity matrix, which we have from a theorem earlier today. That was, again, I think still theorem 7. And then you also have matrices C and D so that you can multiply them on the left and right of A and get the identity matrix. And you also have that A transpose is an invertible matrix as well. Oh, we haven't necessarily proved all of these. We've proved a lot of them. Notice that not every single one of these directly implies the other. So like, for instance, K somehow implies that. And like, we haven't really covered that. Is that directly true? So what I've got for you is, this is our proof for the IMT, invertible matrix theorem. And some of them we've done. So like D goes to I. Let's see, D was, A has n pivots, goes to, A is row equivalent to I. We haven't formally proved that, but I did a lot of reasoning throughout this lecture that would prove that. C goes to D. That would be the columns of A span Rn is the same thing as A has n pivot points. That was theorem 1.4. E goes to F, or E implies F. That means the homogeneous equation, AX equals 0, only has the trivial solution, implies that A, the columns of A, form a linearly independent set. That's just the definition of linear independence. And then, yeah, so look at this, convince yourself that the things I have filled in are true. The ones that have question marks, I am going to make you prove some of these in your worksheet that you're going to have that go with this lecture. And then we have theorems like this theorem right here. That one's missing. I believe we develop a theorem for it in 2.9 is where we're going to get that theorem. So take this drawing and be sure to keep updating it with where you get justifications for each step. Because once you have those filled in, you can use those. Like if I were to say, how can linear independence relate to pivots? Well, you just sit here and you're like, oh, I follow it around the circle like that. I used exercise here, and then this was a theorem, and then, you know, like that. Is this the only way to prove it? No. We could prove this with what we have right now, but it would have had like more tiny circles and stuff. Like you'll notice this has its own little loop down here. And if we had more little loops like that, we could have done it. But I personally thought it was less straightforward that way. You can look at the book for their take on it, and you can probably see what I mean by, yeah, they had some smaller loops and they weren't always very intuitive. Yeah, so go ahead, I encourage you, look at the book. Let's see, I was going to say something else, one more thing. Oh, so another reason to keep track of this, though, is we are going to add on to it in a little bit. Also, I think lecture 2.9, because we're still not done with it. It's still growing. Theorem 1.4 just will not go away. It won't stop. Okay. And I think that's all I've got for you guys. Look forward to helping you guys with this worksheet. Bye for now.